So we know what apparent weight is from the previous model. We did the little activity where we rode in the elevator, and we saw that our apparent weight could be less than, equal to, or greater than our true weight, depending on the motion or the acceleration of the frame of reference, which was the elevator. So we started off discussion of this learning goal by looking at the footage of Chris Hadfield in space in the International Space Station, clearly in what we would call a zero-G environment, because water is floating around, the bag he was holding, everything's floating around, including him. Yet, we could easily do a calculation, and it says in the textbook as well, that G is not zero at the International Space Station. Like he's still well within Earth's gravitational field. And our evidence for that is that he's orbiting the Earth, right? So G couldn't have a value of zero, and if G had a value of zero, he wouldn't be in orbit. He'd be out in the middle of space somewhere, right? So the fact that he's in orbit means that he's well within Earth's gravitational field. So how do we reconcile the fact with that? The fact that he appears to be floating, so we would assume G might be zero, yet he's well within the Earth's gravitational field, and G is like 9.1 or 9 or something at that point, at that altitude. So the answer is, and we illustrated this using that little simulation where it fired the cannon with a horizontal velocity, the cannonball, and then they showed the curvature of the Earth. So here's the cannon, or here's the Earth. There's the cannon, it fires a cannonball, and if we fire it with a little bit of initial velocity, it does that, right? A little more initial velocity, it does that. At some point, we'll fire it with just enough. Oh, not enough that time. Okay, it landed. So we'll fire it with just enough initial velocity that it will go around, and it will keep going around in orbit, right? Fire it with too much, and it escapes Earth's gravitational field, and it never comes back. Okay, so we see that orbit is really just pushing PM2, or projectile motion, to its limit, right? So getting that exact right velocity such that it's always trying to fall. So here's our object in motion. It's always trying to fall to the center of the Earth, but it never reaches there because every time it moves towards the center of the Earth moves in relation to it because it's in orbit. So the force is Fg, obviously, universal gravitation, which is always acting on it, attracting it to the center. Okay. So, so the apparent weight of an object, which is in free fall, and we saw this in the demonstration, we dropped the scale with the brick on it, and we saw the scale go to zero as it fell, right? Hence the normal force goes to zero, and that's what we really call the apparent weight. So the apparent weight of an object goes to zero when it's in free fall. This object is in perpetual free fall. It's always falling towards the Earth but never reaching there, and that's what Chris Hadfield's doing as he goes around the Earth. So that covers the apparent weight part of that learning goal. For the artificial gravity part of the learning goal, and really that should be 2 learning goals in the future, I think it will be. For the artificial gravity part of that learning goal, we consider a spaceship in space, one of these cylindrical spaceships, and the cylindrical spaceship is turning. And because it's turning, passengers inside will experience non-inertial effects because they're in a rotating frame of reference, a non-inertial frame of reference, and they'll experience what we call a centrifugal force, which seems like it's pulling them out of the circle. But we know that that's not a real force, that's just inertia. It's an inertial effect. But we do know that they're in uniform circular motion. Let's say that the ship is moving like this. So we do know that there must be some force keeping them in the circle. And what force keeps them in the circle here? What force is it keeping in the circle? Yes, the normal force exerted from the ground onto them. So there's our centripetal force. There's our centripetal acceleration. There is no force driving them out of the circle. Okay, that's just a fictitious force, centrifugal force, due to the rotation of the frame, the non-inertial nature of the frame of reference. Okay, so next step. And a question like this would be, you need to figure out, well, when we did in class, you need to figure out the period of rotation of this ship, and let's go with that. Well, let's find the frequency of rotation. Just mix it up. You got to find the frequency of rotation. But what do we know? Well, we're gonna have to know the radius of the ship. Okay? And what else do we need to know? Well, let's just go ahead and we'll see. We'll fill things in as we need to go. Just know that you would know enough at the start of the question to do it. But all these questions are the same. Doesn't matter what you're looking for. These sorts of problems, they're all set up the same way. Diagram, free-body diagram, apply Newton's second law. So Newton's second law says the sum of the forces is the mass times the acceleration, which is centripetal. That would be normal force. Oh yeah, the thing you need to know here is what kind of gravity are we getting on this space station? Are we getting Earth-like gravity? Let's say that we're getting half Earth-like gravity because we're trying to save power, right? So let's assume that all you need is half Earth-like gravity to sustain your bone mass and your muscle mass. So they're cutting power. They're going half Earth-like gravity. So we want 1/2 Earth-like gravity. So we'll make that substitution v squared over r for the acceleration because we're talking about uniform circular motion here. All right. So on Earth, if you're standing on Earth, then we know that Fn equals mg, right? For half Earth-like gravity, what would Fn equal?
Half of mg?
Yeah, a half of mg. 1/2 of your weight. That's what half Earth-like gravity would be. So that equals mass over r, and then we're going to make
you end up getting 42 million meters, and then you have to subtract the radius of the Earth.
we could have just gone 2 pi r f there, but I did it that way, so whatever. Mass drops off both sides, so we have 1/2 g equals 4 pi squared r squared over r t. Lose those.
Would
1/2 g
would that not be t squared?
t squared, thank you. 4 pi squared r over t squared. And we need to know the frequency, right? So let's make that substitution. So 1 over t squared is frequency squared because 1 over the period is equal to the frequency. So 1/2 g equals 4 pi r squared f squared. So our frequency squared will be g over 2 times 4 pi r squared. So f squared will be g over 8 pi r squared.
Yeah, would it just be r and pi squared and r?
Oh, I totally screwed that. Yeah, you're right. See? I did that on purpose because then I was into dimensional analysis to show you that it's wrong. Ruined it. Do you believe that?
No. So pi squared r is what it is
Wait,
actually.
hold on a second. So pi squared. See, now you got me all flustered. Pi squared, pi squared, pi squared, pi squared. Okay, is that right? Let's do dimensional analysis, all right? For yourself. Make sure. All right. Okay, so on the left side, we've got frequency squared, right? Which is 1 over period. So it's 1 over time squared on the left side. On the right side, we've got meters. We've got distance, length over time squared. Over, down here, we just have a length. So those go away. And we get 1 over time squared equals 1 over time squared. Okay. Now, dimensional analysis doesn't tell you all the time if you're right. I mean, it tells you you're probably right, but you can see some of these things don't have dimensions, right? So I forgot to square that pi. Dimensional analysis isn't going to catch that because pi has no dimension, right? So if you have errors in your dimensionless quantities, you're not going to catch them with dimensional analysis. So it's not like 100%. But definitely if you have errors in your quantities of units with dimension, it's going to tell you that you have those errors. So it's still a good thing to do. Okay, so to recap, with these artificial gravity style questions, usually it's a spaceship, something like that. You have to be, you're told, is it half Earth gravity, Earth gravity? Maybe you have to find that. Maybe you have to find what the gravity is on the ship. You'll be given the radius of the ship, or maybe you'll be asked for the radius of the ship. But the setup is always the same. The normal force is your centripetal force. That equals the mass times the velocity squared over the radius. Make your appropriate substitution for normal force depending on what the question tells you. And then make your substitution if you're looking for period or frequency. Get yourself a final equation and solve. How would we approach it if we didn't know what the Earth-like gravity was? Let's say that instead they just gave us a period of rotation and a radius of the ship, and we need to figure out what sort of gravity we have there, a multiple of Earth's gravity. How would we figure that out? How would we figure that one out? And let's introduce just a random variable, call it alpha. Alpha to represent the multiplier of Earth's gravity. How do we solve this? So what's the first step? First step's done. We know what we're looking for. We're making a recording here. Can you know, hey, we're recording, so we don't want to sound like we're, shut your mouth and that kind of stuff. It's supposed to be an upscale physics class. Okay?
Why are we recording?
For Sam.
For the YouTube channel.
Is this going to be on the recording?
Sam, yes.
Yeah.
Are you going to edit this out? You want to come up and do some stand-up or what? Okay. So we've got two given values. This is what we're looking for. We're looking for alpha, and alpha we're just going to call the multiple of Earth's gravity. So is this thing half, in which case it'd be half Earth's gravity? Is it 2, twice Earth's gravity? Something like that. Okay. So we got ourselves a diagram, free body diagram. What's the next step?
Could we?
What's the next step after you draw a free body diagram? It's been the next step for the past 2 years. Huh? Set up the equations. Set the equations. And which laws do you set the equations? Second law. Never changes. It's always the same. So the sum of the forces equals the mass times the centripetal acceleration. What's the centripetal force in this case? Just tell me what the force is. Normal force. So normal force equals MC. All right. So now we want to get this expression for alpha. We want to get alpha into our equation, right? So how are we going to do that? Huh? Yes, that's exactly right. Just introduce a variable for alpha. So the value of alpha will just be the centripetal acceleration over g, where g is 9.8, because we're going for a multiple of Earth-like gravity. If we're going for a multiple of Moon-like gravity, we put 1.62 in there. But we're going for Earth-like, so we put 9.8 there. Now the rest of you guys can figure out. You can find out the expression for AC.
Okay.
We've been doing that for like 3 weeks now.
So because it's Earth-like gravity, it's 9.8.
That's right.
Okay.
That's right.
Otherwise,
So this is saying a multiple of Earth's of mg, where g is 9.81, because that's Earth-like gravity.
okay.
We could also find a multiple of Mars-like gravity, a multiple of Moon-like gravity. Just put the appropriate g's in there.
And on the test, will we get these constants, like on
Yeah,
the
you
formula
never
sheet?
have to
Okay.
memorize constants. Okay. Now the other style artificial gravity problem you could get would be the gravitron. So if you have a gravitron, which is that carnival ride, okay, and in the gravitron, you've got someone in the gravitron, and they're they're stuck to the side. It all starts with the drawing a free body diagram of that person. Okay, so this would be a UCM problem as well, or a UGM problem. So let's draw a free body diagram of this guy. There. Thanks, buddy. So we'll draw a free body diagram of this guy in the gravitron from the side. Okay, so here's the wall of the gravitron. That's the wall. He's stuck to the wall. We've got normal force, which is keeping him in the circle. That's the centripetal acceleration. That's the force causing the centripetal acceleration. That's the net force, normal force. We've got his weight downwards. And what force opposes his weight? Like, why is he stuck to the wall? What force required? What force needs to be there so he'll stick to the wall? That's this force.
Nope, centrifugal force is a fictitious force. That's
What's
not
the
a
force that would act upwards to oppose him sliding down the wall? Yeah, friction, static friction. If the gravitron's walls were made of perfectly frictionless ice, you would never stick to the wall. You would wind up like down at the bottom, like in the corner, stuffed into the corner, going around. You wouldn't be able to stick to the wall because nothing would be holding you up on the wall. Those are equal, and there's no outwards force because centrifugal force is not, it's a fictitious force, it's not real. It's just inertia that would be pushing them against the wall. All right. So same thing, we'll apply Newton's second law. So the normal force would equal the mass times the centripetal acceleration. The normal force.
Okay, so what value do you want to get there?
This equation here tells us that the normal force would be the force of static friction over the coefficient of static friction times that quantity. So if you were looking for the, let's say that you were given the coefficient and the weight. Okay, so you're given this. You're given the mass of the guy. You're given the coefficient of friction. No, let's say that you're given the period of rotation. And you have to find the required coefficient. So you know that the period of this device, you got to figure out what to make the cushions out of so people will stick to it, right? So that means basically you got to find the coefficient. All right, so we know that the force of static friction is balanced with the weight.
No, but this is, but it says the radius.
So those masses go away. So our coefficient will be Rg over v squared. And if you have the period, and you have to know the radius too, obviously. So you could find the speed, because you know that the speed would be 2 pi r over the period. So that gives you your speed. You know r, it's given. You know g, so you can solve for that coefficient. But again, it doesn't really matter what you're solving for. You always draw a free body diagram. You always set these equations up. And then you get to an equation, then you would rearrange appropriately, substitute your values. So no matter what they're looking for, it's always the same style problem, right? Identify your centripetal force. Okay, and there would be, other variations on a problem like this, but this is a general style problem you would face. Any questions? Good?
Yeah.
Okay. Sound recording.